Okay, welcome to episode 7. And in this episode, I'm going to talk a little bit about the 6809 CPU. I'll cover the pinout of the 6809 and talk about the various inputs and outputs, what they do, and how to connect them in a circuit. And then I will run through designing and building a free run circuit for the 6809 and show how we can test it to convince ourselves that the 6809 is working correctly. Okay, let's get started. Okay, so the 6809 CPU was introduced by Motorola in 1978. It was famously used in the TRS-80 color computer, and that's the first computer I had, so this is a bit nostalgic for me. And compared to the other 8-bit CPUs of the era, the 6809 is arguably the most advanced, and it has some 16-bit features. It has very flexible addressing modes. It's relatively pleasant to write assembly code for. There are a number of variations of the 6809 you should be aware of. One thing to note is that there is the E variant, the 6809E, and those require an external two-phase clock, and I would avoid getting those just because of the need for the external clock circuitry. So everything I'm going to present is going to assume that you have a normal 6809 and not the 6809E. Several companies made 6809s. The original was Motorola. Those chips will have an MC prefix. Hitachi made 6809s. Those will have an HD prefix. And there are some others. Apparently, Thompson Semiconductor made them, and those have an EF prefix. The 6809 was also available in various speeds. The normal one allowed bus frequencies up to 1 megahertz. The A variants could go up to 1.5 megahertz. And the B variants could go up to 2 megahertz. There was also a fancier CMOS version of the 6809 called the 6309 that was made by Hitachi, and these are quite nice if you can find them. They consume a lot less power and produce a lot less heat because of the CMOS technology. They are completely backwards compatible, but you can run them in an enhanced mode that gives you additional instructions and faster execution. And you can also clock these at higher frequencies. The buses for the C speed grade can go up to 3 megahertz. Okay, so where exactly do you find these? The ones that I have pretty much all come from eBay, and they're not hard to find. I would expect to pay, maybe $5 or $10, that sort of range for one. But you do need to be careful on eBay, and if you see listings that are where the parts are marked as brand new, that's definitely wrong. These things are old. They have not been manufactured in many, many, many years. Typically what you're going to get is an old part that was refurbished so that the seller could pretend that is a new part, and it's a pretty shady business, so I would avoid those. If you see listings that say used or socket pull, that's good. That probably does accurately characterize what you're getting. You may find some listings that say new, but new old stock or surplus. Those are potentially trustworthy, certainly more trustworthy than brand new. So now let's talk about the pinout of the 6809. So here's a diagram of the 6809 and its pins, and I will briefly talk about each pin or group of pins and the function that it plays. So we'll start with pins 1 and 7. Those are the power pins. Pin 1 is the connection to ground. Pin 7 is the connection to the positive supply voltage, which is going to be 5 volts. So those just get connected to your power rails. The reset pin, when driven low, this forces the CPU to reset itself, and that signal should be provided by your power on reset circuit, and we talked about power on reset in the previous video. Pins 38 and 39 are part of the clock generator, and those get connected to a crystal and 2 capacitors, and the oscillation of the crystal provides the frequency that synchronizes the internal operation of the CPU. The Q and E outputs, these are the bus clock signals, and those will oscillate at 1/4 of the frequency of the crystal in the clock generator circuit. And basically, the role of Q and E is that they synchronize bus transactions, and we'll see exactly what they mean and how they operate when in a future video when we talk about glue logic. But essentially, they have to do with letting peripheral devices know when it's time to communicate with the CPU. The read-write pin also has to do with communicating with external devices, and specifically it indicates for bus transactions what the direction of the bus transaction is. And so when the signal is high, it means that the CPU is going to be reading from the bus, meaning reading from a peripheral device, and when the signal is low, it means that the CPU wants to write data to a peripheral device. Pins 5 and 6 are the BS and BA outputs, and essentially together these communicate to the glue logic the current internal state of the CPU, and potentially this can be used to allow multiple devices to share the same data bus. We will not actually be using those in our circuit. The halt input, when driven low, causes the CPU to halt. Essentially, it freezes in its current state, and then when halt is deasserted, then the CPU resumes normal operation. We won't be using that input. We're just going to tie it high so that it's not asserted. The MRDY input, when not asserted, meaning driven low, causes the current bus cycle to be stretched, and that is useful for accommodating slow peripheral devices. We will not be having any slow peripheral devices in the circuit, and so therefore we'll just tie it high to make sure that it's always on and the clock cycles, bus cycles execute normally. And then the DMA BREQ input, that is used for both direct memory access, and I believe also it is useful for implementing DRAM refresh. Neither of those is going to be an issue for us, so we will just tie that high and make sure that it's not asserted. Pins 2 through 4 are the inputs for external interrupts. Pin 2 is NMI, the non-maskable interrupt. Pin 3 is IRQ, the normal external hardware interrupt. And Pin 4 is FIRQ, which is the fast external interrupt handler. For now, in our free run circuit, we're just going to tie all of these high, meaning no interrupt is going to be generated. Eventually, when we build the real circuit, we will support interrupt handling, and we will use at least one of these inputs. Pins 8 through 23 form the address bus, and the address bus is extremely important because essentially these 16 outputs form a single 16-bit memory address, and that is fundamentally how the CPU informs the circuit which peripheral device it wants to talk to. It outputs the memory address of a location within the overall 16-bit address space. So these are going to be really important when we design the glue logic, because essentially we will be decoding the addresses that are generated in order to figure out which device the CPU should be talking to. But for now, in our free run circuit, we're not really going to be using these values directly, and you'll see why when we talk about the free run schematic. But we will be testing to see that appropriate signals are generated on these address outputs. Finally, pins 24 through 31 are the data bus, and these 8 pins can either read a single 8-bit value from the data bus or can write a single 8-bit value to the data bus. And that's very important to understand, that these are bidirectional pins. Sometimes they are inputs, sometimes they are outputs, depending on whether the CPU is trying to read data from a peripheral device or write data to a peripheral device. And when reading data, this can be both because there is an instruction that's just trying to read a data from memory, it's a memory fetch, but then also it's important to realize that the way that the CPU gets the instructions that it's going to be executing is also by reading data from a peripheral device, typically a ROM. So as we'll see with the free run circuit, we're going to arrange that whenever the CPU tries to fetch an instruction from memory, we're going to force a particular bit pattern to be presented to the data bus in order to inform the CPU to execute a very specific instruction. And we'll talk about that a little bit more when we see the free run schematic. But yeah, this is the data bus, and this is fundamentally how data gets into or gets out of the CPU. Okay, so let's talk about what our free run circuit is going to do. And basically, in the free run circuit, we are going to use resistors connected to the data lines D0 through D7 to force the CPU to read hexadecimal 1, 2, that's actually the decimal 18, 16 plus 2, which corresponds to the NOP instruction for all memory locations. So in other words, regardless of what address the CPU generates when it attempts to read a memory location, it's going to read this specific value, which corresponds to the opcode of the NOP instruction. All right, so what exactly is the CPU doing when it starts up, meaning that it has just come out of reset? What it's going to do is it's going to fetch a 16-bit address from the memory at memory location FFFE. That is a hexadecimal base 16 address. That's basically the almost the very highest address in the address space. And the 2 bytes that are read from that address are the reset vector, meaning the address that the CPU is going to start fetching instructions from when it begins its normal operation. And in fact, whatever value is read from the reset vector is simply loaded into the program counter. And once that happens, the CPU is doing its normal mode of operation, which is repeatedly fetch an instruction from memory at the address based on the current value of the program counter register, and then execute that instruction. So given that every single memory location that the CPU reads from, due to these resistors that we're going to set up, is going to read the opcode of the NOP instruction, effectively what the CPU will do is execute an endless sequence of NOP instructions. And the NOP instruction means no operation. It basically does nothing. And so that's what our CPU will do. It fetches a NOP at its current memory address as specified by the program counter, executes it by doing nothing. The program counter automatically increments to essentially move to the next memory location, and then it'll read another NOP instruction, execute that, increment the program counter, execute another NOP instruction, and so on and so forth. So we get this. We get the CPU executing this endless sequence of NOP instructions. Okay, so why the heck are we doing this? Like, what is the point? And the point is very simply to just see if the CPU works. In other words, we want to do the absolute minimum that we can to observe the CPU, executing code. This is the easiest way to do it. And there's an important principle here that I think will be very useful, as we design and build microcomputer circuits, is that we want to make our units of progress as small as possible. We want to just do a little bit that will move our project forward and then test it thoroughly. And this is sort of the very minimum that we can do to just observe the CPU executing code and essentially behaving like a CPU. And what we'll see is that there's things we can do to test to see what the behavior of the CPU is, and that will be interesting and useful. All right, so here is our 6809 free run circuit. I am using the MAX 708 chip to generate a power on reset signal. You can use whatever approach to generating power on reset you want. Just make sure that an active low reset signal is sent to the reset input of the 6809 when the system is powered on. Here is the crystal and 2 capacitors that are going to be used to generate the clock frequency. I used a 3.6864 megahertz crystal. Anything in the range sort of 2 to 4 megahertz should be perfectly fine. You need a couple of 22 picofarad capacitors. And the interesting thing and important thing in the free run circuit is here on the data bus pins. we are using 2 pull-up resistors and 6 pull-down resistors, and the values I used were 4.7K. They just need to be something kind of reasonably large. The configuration of these resistors guarantees that whenever the CPU reads a memory location, it's going to see the value hex 12, which is decimal 18, which is the opcode for the NOP instructions. So every time the CPU fetches an instruction, it's going to be a NOP, and you can see we're completely ignoring all of the address lines, meaning we don't even care what the address is. That is the value that's going to be read whenever the CPU tries to read a memory location, and that is what generates this endless series of NOP instructions that the CPU is going to execute. All right, so what exactly are we expecting this free run circuit to do? And there's an important point here, which is that anytime you design and build a circuit, you should be able to make some predictions in order to have some testable hypotheses that will allow you to confirm whether or not the circuit is actually working. So here are the predictions that I am going to make. I'm expecting to see the Q and E outputs of the CPU oscillating at 1/4 the crystal frequency. So given the 3.6864 megahertz crystal, that means we should see 921.6 kilohertz as the oscillation frequency on those 2 outputs. As I probe the address pins, A0, A1, and A2, and so forth, I'm expecting that as I go from one to the next, I should see that the frequencies decrease by a factor of 2 each time. And the reason I'm expecting this is because if you just kind of think about the CPU fetching these NOP instructions one after another at memory addresses, that are counting up by increments of 1, that's just the pattern that we should see. And so, for example, here is an example of just counting from 0 to 15 using 4 address bits. And so here's 0, here's 1, here's 2, here's 3. And if you just kind of think about how the bit patterns change as we increment these binary addresses, the least significant bit, A0, is going to toggle every single time we increment. So we get 0, then 1, then 0, then 1. A1, the next most significant bit, toggles only half as often, so we get 2 zeros and 2 ones and 2 zeros and 2 ones. And then if we go to the next significant bit, it's once again it changes only half as frequently, so we get 4 zeros and 4 ones and 4 zeros and 4 ones and so forth. And if we think about these changes as being square waves, then what we should see is that the frequency of those square waves is going to halve each time we move to the next most significant bit. We could make some other predictions. So for example, if we could observe all 16 of the address lines right when the CPU comes out of reset, we should see it fetching the reset vector at addresses FFFE and FFFF. Those are the 2 highest memory locations in the address space. Okay, so let's see if we can test some of these predictions. All right, so let's see if we can verify whether or not our free run circuit is working. And I've built the free run circuit on the breadboard here exactly according to the schematic. And the hypotheses that I made were essentially about frequencies of oscillation I was expecting to observe on particular output pins. And we could certainly visualize those signals on the oscilloscope, and oscilloscopes are fantastic if you want to visualize changing voltages over different time scales. Of course, oscilloscopes are potentially expensive. Not everybody has one. A really nice option that is very inexpensive is to use the frequency function on your multimeter. So here's one of my multimeters. It's a Zotex ZT102. This is also the same multimeter as the Aneng 8002. Just fantastic little cheap multimeters, wonderful for low energy applications like these little 5-volt digital electronics projects. Highly recommended. I would suggest getting a few of these. You won't regret it. All right, so let's try to observe some of these frequencies. So I'm going to put my ground probe on the ground pin, and I'm now going to check the Q output. And as predicted, we see 921.6 kilohertz. If we test the E output, we see exactly the same, 921.6 kilohertz, so that's wonderful. If I probe A0, the lowest bit of the address bus, looks like I'm seeing 230.4 kilohertz. So if I go to A1, I'm expecting to see half of that frequency. And I do. I see 115.2 kilohertz, and then on A2, 57.6 kilohertz, and then on A3, 28.8 kilohertz, 14.4, 7200 hertz, and so forth. So that exactly matches my prediction and gives us, pretty strong evidence that the CPU is indeed fetching NOP instructions at addresses that increment by 1. Awesome. All right, let's do one last experiment to make sure that the free run circuit is working the way that we expect. And what we're going to do is we're going to use this Saley logic clone 8-channel logic analyzer to observe the signals on the low 8 bits of the address bus, A0 through A7. So essentially every time the CPU generates an address for a memory transaction, we're going to capture that the low 8 bits of that value from the logic analyzer. And I should note, what a logic analyzer does is a lot like what an oscilloscope does. It allows you to capture and visualize changing voltages over time. Logic analyzers specifically capture digital voltages, so it's only going to make a distinction between a low voltage and a high voltage. But that's perfectly fine because these are digital signals. And logic analyzers are just in general very useful for working with microcomputer circuits. You can buy these little things for $9 or $10 on eBay or AliExpress. Here is the search term that should get you compatible devices. They work with the open source SIGROC logic analyzer software. Definitely very, very useful to have. All right, so here is what I'm expecting to happen when we capture traces as the CPU comes out of reset. The first thing the CPU should do is to load 2 bytes, specifically a 16-bit memory address from addresses FFFE and FFFF. Those are the memory locations of the reset vector. So given that we're only capturing the low 8 bits of the addresses, essentially we should see the values FE and FF hexadecimal being generated by the CPU. We should see those in our trace. And we know that because the data bus is wired with these resistors such that the only possible data value that the CPU can actually read is hex 12, that will effectively make the reset vector hex 1212. So that should be where we expect to see the CPU to start fetching and executing instructions from. That's basically the address where the first NOP instruction is going to be loaded from. And once the CPU actually starts running and executing this endless series of NOP instructions, we should see a binary counting pattern, counting up by 1 pattern, produced on the low 8 bits of the address bus. Okay, so let's fire up the logic analyzer and see if that's what happens. All right, so here is Pulse View. That is the GUI for the SIGROC logic analyzer. And we're capturing signals from our Saley logic clone. We're going to capture 5 megasamples at 12 megahertz. Our bus frequency is going to be a little less than 1 megahertz. So 12 megahertz, should give us decent resolution, adequate to capture the waveforms that we're interested in. And we're going to be capturing the 8 traces corresponding to our A0 through A7 signals. And I've added a parallel decoder that will decode these 8 single bit data points into a 1 byte value, and essentially we can see the exact address values, at least the exact the low 8 bits of each address value as the CPU generates them. Okay, so let's see if we can capture some signals. So I'm holding down the reset button on my free run circuit, and I'm going to start capturing from the logic analyzer, and then release the reset button, and we should see the CPU come out of reset. Okay, so I think I got it there, and you can see here that we have captured some data. So let me zoom in here, and we'll see what we see. Right, so Okay, good. So you can see the low 8 bits of the address line, toggling here. And notice here in the parallel decoder, the first value we see is FF. We're actually missing a decoded value that actually occurs earlier, because you can notice here that D0, which corresponds to the A0 address line, actually is low. So there is a point in time where all of the bits except D0 are high. That does correspond to the hexadecimal value FE. So that is consistent with seeing the CPU fetch the 2-byte reset vector from addresses FFFE and FFFF. We're just missing a decoded value here. And what we also see that is quite significant is that we see the binary counting pattern that we are expecting to see starting from hex 1, 2. And that is consistent with seeing the reset vector address being 1212, meaning that that's the address that the CPU is going to start executing instructions from. And if we zoom out a little bit, we see this very characteristic count by increments of 1 pattern on the low 8 bits of the address bus, and that is completely consistent with the CPU generating one address after another in sequence as it executes this continuous sequence of NOP instructions. So everything we're seeing here in the logic analyzer seems perfectly consistent with our expected behavior. Okay, so that wraps up for this video, and hopefully I've convinced you that building and testing a free-run circuit is useful. It allows us to verify that our CPU actually works. It also allows us to verify that our power-on reset circuit works. And I think this is also really useful because this is a really good opportunity to practice using some of your basic testing tools like the multimeter. We saw the multimeter being used in frequency mode. It also gave us an opportunity to use a logic analyzer, and we found out some useful information about the behavior of our circuit. In our next video, we'll start talking about designing a memory map for our computer and the glue logic for our computer. This is really, really important and fundamental, and this is really where it gets fun. So I'm very excited about that. And once we have those things in place, we can start adding ROM and RAM to the circuit, and this is going to become a computer. So, all right, I will see you in the next video.